Welcome to Texas State University's Organic Chemistry 2342, Organic Chemistry 2. I'm your guide, Dr. David Urban, and we'll be continuing with Chapter 13, Part 2, Conjugated Unsaturated Systems, specifically with conjugated dienes. So the first thing we need to think about conjugated dienes is that it has the consistent structure of having two double bonds joined by a single sigma bond. And so they are typically called 1,3 dienes, and they're in conjugation because the pi from one double bond can overlap with the other double bond, giving us different reactivity. We have three possible stereoisomers available to us in 1,3 dienes if we have alkyl groups attached to the ends of the chains. The first one we have is what we can have two of the trans double bonds, giving us a trans-trans 1,3 diene. Now remember, when you review chapter 7 for E and Z rules, E is similar to trans and cis is similar to Z. Okay. The other possible stereoisomer is the cis-cis diene right here. And then we also have the possibility of a cis-trans diene. Okay. Now, we do have conformations available to us in the dienes because remember the sigma bond does have free rotation around it, the pi bonds don't. So once a pi is in the cis, a double bond is in a cis configuration, you have to break that double bond to get it out of the cis configuration. But the sigma bond can rotate. And so we can have what we call an S-cis conformation where the sigma bond rotates and the two double bonds are on the same orientation with each other and overlapping again, or we can have what we call the S-trans conformation where the double bonds are away from it, but still in conjugation with each other, okay? So that means we have stereoisomers of discrete molecules, plus we also have conformers that can be interconverted between them. So for example, the cis-cis isomer and the trans-trans isomer, those are set because the double bond cannot freely rotate. However, you can take your trans-trans isomer and rotate around the sigma bond and go to the S-trans configuration as shown here, or the cis configuration here. Notice that we have not broken any double bonds. All we did was a rotation around this single bond here in the middle to get them either opposite, the two double bonds opposite each other in the trans, or two double bonds near each other, the cis configuration. Okay, so let's talk a little bit about the features of these dienes. The first thing we need to think about is that the reactions of these conjugated dienes are different from reactions of isolated double bonds. Okay, we'll see a lot of different types of addition reactions and or substitution reactions. The other thing we need to know is that these conjugated dienes are more stable, i.e. they have higher heats of hydrogenation than isolated dienes. That means that there is definitely some overlap. There is an electronic interaction between those two dienes. The conjugation between the diene absorbs longer wavelengths of ultraviolet light. What that means is because it is conjugated, it takes less energy to excite electrons from a bonding orbital up into an unoccupied orbital. Now, the carbon-carbon sigma bond between the two double bonds is shorter than it would be in other systems. Okay, so what we see here is that that partial double bond character associated with conjugation gives it a shorter bond than would be expected. So let's look at that as a function of its resonance contributors. So our major resonance contributor, as we learned from the last video, is the one that does not have charge separation and has the highest number of bonds right here. However, the fact that we have the possibility of having a charge separated contributor and a separate charge separated contributor, we have two minor contributors. However, they do contribute enough to see the partial double bond character in this middle sigma bond, and because of that, it is now a shorter bond because of that partial double bond character. Okay, so let's talk a little bit more about UVVis right here. So ultraviolet visible spectroscopy, or UVVis, actually tells us a lot of information about double bonds. Okay, so in the case of UV, that's these shorter wavelengths between 800, 180, and 400 nanometers. And then once we get into visible wavelengths where we have 400 to 780 nanometers, that's where we start to see, okay? And so what's happening there is we have the electrons that are in the outermost shells, or highest occupied orbitals here, can be excited into empty shells above it using the light energy that hits upon them. Okay, so that means the stronger the bigger the gap between there, the more energy it's going to take, and therefore strong absorbing pi bonds, strong absorptions for those pi bonds because they're further out, and we have weaker absorption for lone pairs. Okay, so then we also have the idea of the concept of what a chromophore is. A chromophore is the portion of the molecule, for example, the conjugate diene, that absorbs UV or visible light. And it also gives the color, it changes the color of the compound, hence the word chromo in chromophore. Not all parts of the molecule have to absorb light to have it have color, only the section that does. That section is the part that's called the chromophore. All right, now we don't have to worry too much about homo-lumo interactions. All we have to know is that because of the energy of these orbitals right here, the more conjugated it is, the less energy it takes to excite an electron into that higher orbital. Okay, so let's talk about a little bit about some other components related to the spectroscopy. The first thing is we can use Beer's law to tell us a little bit about the molecule itself. So the absorbance is how big the peak is, and it's related to what we call the molar absorptivity. So the molar absorptivity is basically each individual molecule will have a different molar absorptivity, and basically it relates to how the molecule absorbs light. Does it absorb it very well or very poorly? Okay, so if you have a high extinction coefficient, that means it absorbs a lot of light and gives off a much bigger absorption signal. And if it has a very small molar absorptivity, then you would have to have a lot more of the material in the solution to be able to see that. The next component is actually the wavelength of light at which it absorbs. And that's the energy it takes to take that one electron from an already occupied orbital to excite it into an unoccupied orbital above that energy. So you have to add energy to the system, it'll excite, and that excitation is the absorption we see. So the presence or absence of a peak in UVVis spectrum is used to determine the presence or absence of double bonds or multiple double bonds in a compound, okay? And typically, the more conjugated the double bonds are, the longer the wavelength and the lower the energy at which it takes to do that excitation. Okay, so if we look at this from a perspective of extending conjugation should give us longer wavelengths or lower energy, let's go ahead and start with just ethylene here. We see that it has a lambda max, or a maximum absorption around 170 nanometers, okay? That's outside of UV. UV starts at 180, so we don't see a UV signature for ethylene itself. However, if we add a couple other carbon bonds to that ethylene, it brings it barely into our UV at 184 nanometers. And then by looking at isolated single and double bonds, we have them all approximately in the same range here, just barely absorbing in the UV, if it's absorbing at all. Now, once you added a second one in conjugation, we actually lower the energy into the 200 range here. So those are all double bonds or double and triple bonds in conjugation with each other. That lowers the energy necessary for that light to be absorbed and excited. And then we can see that, so those conjugated double bonds have a lower energy of excitation, which means they are conjugated. Now, if we break conjugation by adding a single sp3 hybridized carbon in there, we lose that advantage. It goes back to being the same as if it was an isolated double bond. Okay, now, when we take that and constrain the system such that it has to have pi-pi overlap in the systems, like in these ring systems, or extend the conjugation, it actually takes even less energy to absorb that light, and therefore it's at longer wavelengths and approaching more and more toward the visible spectrum. So that concludes Chapter 13, Part 2. dienes and UVVis.